Thank you for being here and for all the great talks we've seen yesterday and today. I'll be talking about some work on slantwise convection in the Irminger Sea with my co-authors who are listed here. So I'll start off getting pretty much into the specifics here, since this is an expert audience, and talk about how, we tend to think of the AMOC lower limb as being formed via heat loss in vertical mix layers. And here's one example from a study by Tilis Petit from last year, focusing specifically on the eastern subpolar gyre. And what they found in this study is that the air-sea buoyancy forcing, in this box, pretty well matches the net transformation in this region. So, the heat that's lost in these mixed layers that are of density lower than the isopycnal of maximum overturning form about the right amount of water. However, the link with variability is pretty unclear in this study. So they found in the mean that these numbers match up, but they need to invoke large storage and can't quite explain the time variability. I also wanted to point out that there's pretty big error bars on all of these numbers here in the center. Okay, so what I'm going to be talking about is evidence for another transformation mechanism in the western boundary current of the Irminger Sea to kind of add to this way that we look at how the AMOC lower limb is formed. And for a little bit of background on the boundary current of the western Irminger Sea, I have here a figure from one of my papers last year showing this water mass that I named Upper Izzy water to kind of think about it as a parallel to Upper Labrador seawater. So this is water that forms near or in the boundary current that's lighter than the big convective water mass that's formed in the interior of the Irminger Sea. And so in this top panel here, I'm showing PV in color, and you see these seasonal pulses of low PV water in the boundary current. And a few intriguing things about this is that we see these pulses in the boundary current below the mixed layer. So this tiny gray line that you can't really see here is the mixed layer in the boundary current. So there's this low PV water that looks like something that's sort of convectively formed or well mixed because of its low PV, and it's in the boundary current, it's below the mixed layer, and it projects directly onto seasonal AMOC variability because it's in the boundary current where it's being exported right away. It has a very clear link with that variability on these kind of shorter timescales. But what wasn't entirely clear in this study was, how this is formed. We have some sense that it's similar density to water in the mixed layer that's just offshore of the boundary current, so not at the sort of maximum velocity area, but a little bit offshore. But it wasn't totally clear how this is getting into the boundary current, what's triggering its formation. So in this study, we're looking into that more, and now with 4 years of data instead of 2. Okay, and leading hypothesis is that it's formed by slantwise convection. So before I get into showing you the evidence, I'll give you a bit of a primer on what slantwise convection is. So this schematic I find very useful from Hain and Marshall. And on the left, we see the picture that we're probably all mostly very familiar with here, which is a cooling ocean where you have these isopycnals. They're these horizontal lines. So it's well stratified below the mixed layer. And within the mixed layer, we have these gravitational instabilities that are formed when you cool the water, it sinks. And you get this homogeneous vertical mixed layer of constant density. Symmetric instability, and slantwise convection is a response to symmetric instability instead of gravitational instability. So symmetric instability can happen when you have cooling, for example, but you also have strong horizontal density gradient. So you don't have this sort of idealized homogeneous ocean, but you have this gradient of density. So that's shown with these sort of tilted vertical lines here. And just to walk you through a little bit more of what symmetric instability is that's triggering this slantwise convection, we can look at a pretty general form of PV here. So you have, planetary relative vorticity multiplied by the vertical buoyancy gradient, and then a term that is dependent on the horizontal density gradient and shear, which are kind of equivalent through geostrophy. So when you have this combination of very weak vertical buoyancy gradients and strong horizontal density gradients, you can actually get negative PV, which triggers a symmetric instability. And this sort of slantwise mixing that creates a zero or low PV layer that's actually stratified. So this whole wedge here has very low PV, but it actually is stratified. So you'd see this low PV signal, but it would be below what you would conventionally define as the mixed layer. And this kind of scenario can come up when you have down front wind forcing. So I'll show that here. Okay, so here I'm showing now with the arrows, this is a winter and spring wind stress from ERA 5, and then in the blue colors is SSH, just to give you a general sense for the circulation. And in purple, I'm zooming into the OSNAP moorings here in the western Irminger Sea. You can see there's this large, strong boundary current. I'm showing some density contours in the thick black lines. And when winds blow down this front, you have an Ekman flux that's onshore. So that brings the denser water that's offshore on top of lighter water onshore. And that can trigger this sort of slantwise convection in response to this forcing. Okay, so one thing we can do is quantify how big this forcing is compared to the air-sea buoyancy forcing. So this Ekman buoyancy forcing from the downfront winds can be quantified using the wind stress that's along the front, the buoyancy gradient across the front, and then normalized by some constants. And then I can get the air-sea heat flux into the same buoyancy units, like this. And the reason I'm doing this in buoyancy space instead of heat flux space is because this Ekman buoyancy flux is actually, it's more like brine rejection than cooling, because you're bringing this salty Atlantic water on top of fresh polar water, which is kind of an interesting side note. So right away, you can see that this panel for the cumulative Ekman buoyancy forcing, these lines are much larger than the air-sea buoyancy forcing. You can also see that there's a large gradient across the boundary current. So this dark blue is CF4, which is most onshore, and then these really light colors are CF6 and 7, which are further offshore. And the reason there's this big gradient is because there's a big change in the density gradient as you move offshore. Okay, so this gives us a sense that this Ekman buoyancy forcing, could be potentially very significant over the boundary current. It looks to be about 4 times as big as the air-sea buoyancy forcing over the boundary current. And now in this plot here, I'm showing that there's actually a subsurface response to this Ekman buoyancy forcing. So in the top panel, I'm showing a time series of the Ekman buoyancy forcing, and positive Ekman buoyancy forcing, shown in black, is going to be the forcing that would extract PV, or the forcing, that's sort of analogous to cooling or brine rejection. The second panel here is the mixed layer. And I mostly have this here to highlight that the next 2 panels are usually below the mixed layer. So the bottom 2 panels are PV, at 375 meters, and then at 625 meters. So the mixed layer, in the first few years, it's sort of around 300 maximum. In the second 2 years, it's below 450. So definitely this bottom panel is always below the sort of conventionally defined mixed layer. And then in gray, in these gray vertical lines, I'm picking out events where this buoyancy forcing goes above this vertical dashed line. And you can see that where we have this Ekman buoyancy forcing, we also pretty commonly have drops in PV, which we would expect, which is consistent with a slantwise convection kind of response. And again, these are well below the mixed layer. And you can also see that often there's an increase in PV before there's a decrease. And that can be explained better, perhaps, if I show you the next slide. So the next thing I do is take all of these gray vertical bars and put them together into a composite. And I look at the first and the last day of this composite slantwise convection event. So the top panel is salinity in the colors, and then the bottom panel is PV. And on the first day, you can see that this really fresh water from the shelf has sort of come offshore. So that would tend to generally increase the PV. And by the last day, you have the fresh water has been pushed onshore. Isopycnals are steep. And most intriguingly, in the PV, you see this big drop in PV that's happened right over the boundary current in CF5. So before, you have this high PV everywhere. And then at the end of the event, you have this low PV that's focused around CF5. And remember that the Ekman buoyancy forcing was pretty low out here at CF6 and 7. It was strongest here at CF4 and CF5. So we'd expect this effect to be biggest right around here based on the forcing as well. Okay, and I motivated, looking into this in the first place through this formation of upper Izzy water, which is this water mass that's in the lower limb of the overturning circulation, but it's not the same as the Labrador seawater like water mass that's formed in the interior. And I wanted to understand how it was formed. Interestingly, I should probably explain what this plot is showing first. But the bottom line is that this process does appear linked with the formation of upper Izzy water in the first half of the record, but in the second half of the record, it's not directly forming that same water mass if you use the same density contours, but is still definitely active. So the top panel is potential vorticity in the colors. In black, I'm showing this was the definition of this upper intermediate of this upper Izzy water mass that was defined using these first 2 years. In the second 2 years, you can see that it not as much of it forms, right? And this is linked to the salinity. So the bottom panel is salinity, and we heard from Tiago's talk yesterday that these second 2 years here are getting very fresh. So the whole density structure of the boundary current is completely different in these second years. But despite this, in the stars, I'm showing these Ekman buoyancy forcing events, and in the colors, you can see the PV. So even though you're not forming the same water mass defined by those density limits, you still have these very coherent PV deep responses. The green line sort of showing that 625 meter time series where I showed the response. So you have responses all the way down here, and you're still transforming the water column. You're just transforming it into different densities. So this gray one shows, you're still shoaling these isopycnals. You're just forming something a little bit different in these next 2 years. Okay, so just to summarize, these downfront winds are forcing a PV response in the Irminger Sea's western boundary current. This is well below the mixed layer, and it's not something that's not accounted for in our current thinking of how the lower limb of the AMOC is formed. And it's probably active all along eastern Greenland and also in the western Labrador Sea, just thinking about the direction of the winds and how they're aligned with fronts. Models and reanalysis products don't resolve these freshwater density gradients, so they probably don't include this process. I'll just add the caveat that it's not totally clear how much this process impacts sort of mean AMOC and low frequency variability. And then a final note that I deployed some oxygen sensors in summer 2020 on these Western Irminger Sea OSNAP moorings, and Jamie Palter is leading a big project that has them all over the Labrador Sea. So in the future, we're hoping to also shed light on whether the boundary current is actually being directly ventilated via this process. So if oxygen is getting in with this slantwise convection mixing process. And I will stop there. Thank you.